Hello guys, so today I will discuss about stability and determinacy of structures with computation of reactions for beams, frames, and truss. So here, uh, before we start with the determinacy, let's discuss first the concept of structure. So a structure is considered to be in equilibrium if initially at rest. It remains at rest when subjected to a system of forces and couples. So if you have here considering a certain object, we can say that this is equilibrium if at rest, if initially at rest, it will be at rest unless otherwise it is subjected to a system of forces and couples. So from this, if this object is applied by the different forces, here we can see that there will be some component of forces, whether F1, F2, F3, and F4. The same is true with the moments. So from this, we can resolve the forces into components such as summation forces along X, Y, and Z. The same is true for moments. So we can say that this is equilibrium if all the forces that will act along X, Y, and the moment will be equal to zero. Okay? Uh, in other meaning, we can say that this is equilibrium if the number of unknown reactions is uh, the same with the equilibrium equations. So the term rigid structure as used here implies that the structure offers significant resistance to its change of shape, whereas a non-rigid structure offers negligible resistance to its change of shape when detached from the support and would often collapse under its own weight when not supported externally. So, as structural engineers, uh, we are we are putting members which are rigid because even we detach it from each support for the analysis, it will not collapse. Okay? Then we have the term external forces. These are the actions of other bodies on the structure under consideration. And we can classify it accordingly. So the first one is the applied, usually referred to the loads. Example, live load, wind load, dead load, and other loads. These are the loads that have a tendency to move the structure and usually known in the analysis. Usually these are known, these are given. And the reaction forces, these are the unknowns. Usually these are the forces exerted by supports on the structure and have a tendency to prevent its motion and keep it in equilibrium. Okay, so these reactions are the ones that keep the structure in equilibrium so that it will not move or it will be stable. Then internal forces are the forces and couples exerted on a member or portion of the structure by the rest of the structure. So internal forces can be seen if you cut a certain section. Okay? So these are the different types of support. Roller, racket, link, hinge, fix. So when we talk about roller, the forces that will act is always perpendicular to the supporting surface. So for example here, see, it is projected somewhere here, so the forces will act perpendicular to the surface. Okay, roller, this is the surface, perpendicular. Then link, the force R acts in the direction of the link and may be directed either into or going from the structure. So this link, if you cut it, there will be reaction. Okay, this is like internal reaction. Then hinge, the reaction force R may act in any direction. It is usually convenient to represent R by rectangular component Rx and Ry. Then fix, it consists of two force components and a moment. So these are other type of connection, ideal as symbol, and reactions. So determinacy. The equilibrium equations provide both the necessary and sufficient condition for equilibrium when all the forces in the structure can be determined strictly from these equations. The structure is referred as statically determinate. Statically determinate meaning mm, the equations, the equilibrium equations, for example, summation forces along x, y, and z. For example, there are three equilibrium equations and the number of unknown reactions are three, so it is called determinate. Except otherwise, if if the resultant forces act on a single point, even it is determinate, it will become unstable. So how about statically indeterminate? Sorry, statically determinate if all support can be determined by solving the equation of equilibrium. This is also another meaning. So with the given equations, if you are able to determine the reactions given the equilibrium equations, it is called statically determinate. So indeterminate if there are more unknown forces than the equilibrium equations. For example, if you have four unknowns, then you have only three equilibrium equations, it will become statically indeterminate to the first degree because the number of unknowns is more than by one. Okay? It depends, but the concept here is if the number of unknowns are more than the equilibrium equations. Then if a structure is supported by more than three reactions, then all the reactions cannot be determined from the three equations. So the reactions in excess of those necessary for equilibrium are called external redundance, and the number of external redundance is referred as the degree of external indeterminacy. So whatever excess uh, of those necessary unknowns or equilibrium for equilibrium, it's called external redundance. So stability and determining the structure with computation of reaction beams and frames. Why beams and frames? Because it's the same to the formula will be the same. So here R is equal to 3n, where n is the number of member. Okay. So for coplanar structure, there are at most three equilibrium equations for each part. So that if there is total of n parts and R force and moment reaction component. So R is the number of reactions and N is the number of member. Okay? So recall that an internal hinge can transmit two forces component and an internal roller can transmit one force component. This is critical. You should always identify this one. So for example here, yeah, internal hinge. Uh, the moment AB is 0, the moment BC is 0. Okay? Let's have, sorry. Unlike the, we have some problems here, but I will discuss on the next slides. For the time being, I will move. Unlike the beams and pin connected structure of the previous, frame structures consist of members that are connected together by rigid joint. Meaning, unlike for beam, if it is connected by internal hinge, it is it is it has two reactions. But for frames, if you cut it, you will include also the member. So internally stable structure is considered to be internally stable or rigid if it maintains its shape and remains a rigid body when detached from the support. Internally unstable is internally unstable if it cannot maintain its shape and may undergo large displacement under small disturbances when not supported externally. So what we can learn here is when we talk about unstable, it is non-rigid, meaning if you isolate a certain member, it will undergo a certain displacement. Okay? So improper constraints. In some cases, there are be as many unknown forces as there are equations of equilibrium. However, instability or movement of a structure or its member can develop because of improper constraining by the support. This can occur if all the support reactions are concurrent at a point. This is the one that I'm saying. If all the support reactions are concurrent, okay, it will be improper. Another way in which improper constraining leads to instability occurs when the reactive forces are all parallel. Okay, remember this too. So this is concurrent forces, concurrent reactions. They will meet a certain point O. See? Meaning, why this is unstable? Because all the forces cancelled out. So if reaction at A and C cancels out, meaning at point B, there will be a tendency that this member ABC will move either here or here because there is no reaction that will counteract the movement. So in general, the structure will be geometrically unstable, that is, it will move slightly or collapse. If there are fewer reactive forces in the equation of equilibrium, this is also another unstable. For example here, see, if you have reaction P, this P will be divided into Py and Px. For Py, there is no problem because ABC can support that load Py. But for Px, there is a tendency that this beam will move in this direction and no support reaction will counteract the movement, so it will be unstable. Okay, so let's have example. Let's classify or let's determine the determinacy. So here you have pin 2, 1 roller 1. So there are 5 reactions. How many member we did not cut? So it will be 1. So Rn is 3. So 5 is more than 3. Indeterminate to the second degree. The second one is, this is cable. So if we cut this one, 1, 2, 3, 4, it will be parallel reactions. It will be unstable. Why unstable? If, for example, I will apply a load along X, can this 4 cable resist the movement along X? No, it will move, whether slightly or large displacement, but it will move, so it will be unstable. Let's go to letter C. So you have roller. Again, the reaction is always perpendicular to the surface, 1. Then pin, 1, 2, 3. We did not cut, so N is 1. So this will be statically determinate. Letter D, if you cut this one, 1, 2, 3, 4. There will be N is equal to 2 members. Then the reaction will be 1, 2, 3, 4, 5, 6. Okay? Do not count this one. If you include this one as 1, 2, automatically you are also including the reaction here. Okay? So 1, 2, 3, 4, 5, 6, 6 is statically determinate. How about for frame? Okay? The same procedure. Okay? But here in frame, when you cut it, automatically 3 reactions will be seen, or 3 internal reactions will be seen: the force X, Y, and the moment. So if I will cut this one, back, how many? N is 2, right? 1, 2 members. How many reactions? 3, 6, 9, 10, 11. Okay? So 11 minus 6 is equal to 5. Okay? There is also another shortcut here. Even we will not cut this section, even we will not cut, if we will not cut, N is 1, right? How many reactions? 3, 4, 5. So, reactions is 5, 3, 4, 5. So, it's better to use this one, sorry. It's better to use. I made a mistake. This one is better. The second one is, here, if we cut, is one reaction here. So, 3, 6, 9, 12, 15, 18, 19, 21. minus how many member? 1, 2, 3, 4. 4 times 3 is 12, 9 degrees. How about here, pin? So, I will, I will isolate one by one. 3, 4, 5. 3, 4, 5, 6, 7, 8, 9, 10, 10. Then 3 members, 1, 2, 3. 3 times 3, 9. Indeterminate to the first degree. Okay, how about this one? 1, 2, 3, 4, 5. 5. Then members is too unstable because the Rn is 6. It's more than 5, so unstable. So computation of reaction. So disassemble the structure and draw the free body diagram. Okay? Then recall that reactive forces common to two members act with equal magnitude but opposite direction. Then all two force members should be identified. These members, regardless of their shape, have no external loads on them, and therefore their free body diagrams are represented with equal but opposite collinear forces. In many cases, it is possible to tell by inspection the proper arrowhead sense of direction of unknown forces. Meaning, if you look at the structures, you can directly identify. Okay. So here, for example, we have the beam. Let's determine the reactions along at point A and B. So here you have vertical loads 20, 20, 26. Of course, this 26 can be converted into 2. The vertical, which is 26 times 12 over 13, the vertical, and the horizontal will be 26 times 5 over 13. So we can have summation moment at A to determine By. Okay. By here times 6 plus 6 plus 3, 15 minus 20 times 6, 20 times 12 minus 26 times 12 over 13 times 15 for the vertical component. No need to determine the horizontal component because it intersect the point of moment, so automatically that will be 0. So By is 48 kilonewtons. Then you can now proceed summation forces along Y. We have here AY plus By, which is 48, minus 20, minus 20, minus the vertical component of the 26 kilonewtons, 12 over 13. AY is 16 kilonewtons. Then for AX, you can use summation forces along X. The value of AX is actually the horizontal component of 26 kilonewtons. Okay? It will be 10 kilonewtons. Next. Next. The same. Uh, determine the reactions. This is for frames, okay? So there is internal hinge, meaning you can detach it. You can either use member AB or you can use member BC, okay? So let's assume that we detach member AB, okay? So summation forces along A, okay, will be FBC cosine 45 times 3 minus 600 because 200 times 3 is 600 times the distance between the two, it's 1.5. So FBC is 424.26 newtons. There is also another procedure here. You can also determine BY, okay, BY and BX. By the way, what happened here is FBC is the resultant forces of BX and BY. So summation forces along Y, AY plus the vertical component of BC, 4 to 4.26 cosine 45 minus the downward forces of 600, AY is 300. The same is true with summation forces along X, 300. Then now, if you have already the values, you can now proceed to C. Okay? So if you isolate BC, for example, this is BC. You have FBC here. So CX will be FBC sine 45 and CY is FBC cosine 45. Or you can isolate the whole structure since you have already AY and AX. Okay. Stability and determinacy of structures with computation of reaction for truss. So a truss is a structure composed of slender members joined together at their endpoints. A truss is an assemblage of straight member connected at their ends by flexible connection to form a rigid configuration. So for trusses, if you cut the section, it will have summation forces along X and Y only because it's always assumed that it's rigid and it's assumed that you have only two forces. So king pose, Warren truss, Howe truss, Pratt truss, Pink truss. So assumption for design, the members are joined together by a smooth pin. Meaning, if it is a smooth pin, there is no moment. So all loadings are applied at the joint. Because of these two assumptions, each truss member acts as an axial force member and therefore the forces acting at the ends of the member must be directed along the axis of the member. So you have only two forces, which is uh, tensile or compressive. So simple truss is constructed by starting with basic triangular element. So to identify the determinacy, you can use B plus R is equal to 2J. B is the number of bars, R is the reaction, and J is the number of joint. So the same with beams and frames. It is stable and unstable if the reaction are concurrent or parallel. So classify each of truss as stable, unstable, statically determinate, or indeterminate. Okay. This is stable since the reactions are not concurrent or parallel. Then B is 19 bar. How? Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay? 19. Reactions is roller 1, pin 2, 3. Join 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. B plus R is 2J. 22 is equal to 22. Okay? So here, B is 9, 1, 2, 1, 2, 3, 4, 5, 6, 9. Then the reactions is 2, 3. 3 joint is 1, 2, 3, 4, 5, 6. So, stable and determinate. So, method of joints are used if you want to determine the members or of each considering point by point. So, for example, if you use point B, you have 500 kilonewton. Then you have the forces that will create at FBA and FBC. Okay, method of joint. So for analysis of method of joint, draw the free body diagram. Always assume the unknown member's force acting on the joint free body. Apply the two force equilibrium equation XY and solve for the two unknown member forces and verify their correct directional sense. Continue to analyze each of other joint. Once the force in a member is found from the analysis of a joint at one of its side, the result can be used to analyze the forces acting on the joint at its other end. Remember, in compression pushes on the joint and member and tension pulls off the joint. So, before we go to computation of reaction, let's have here the additional problem for determinacy. B is 8. 1, 2, 3, 4, 5, 6, 7, 8. Reaction is 1, 2, 3. J is 1, 2, 3, 4, 5, 6, 6. So, this is unstable because uh, meaning the number of unknown is less than the number of equilibrium equation, and the tendency is uh, it will move. B is bar is 7, 1, 2, 3, 4, 5, 7. Reactions is 2, 2, 4, 5. The same all three. This one just check. Okay. So determine the force in each member of the roof truss shown in the photo. The dimensions and loadings are shown. State whether the members are in tension or compression. So since we are required to determine the force in each member, what we can say is use the method of joint. Okay. Okay, method of joint. So here, the first thing that you need to do is to determine the reactions of x, y, and dy. Summation forces along x, automatic. The ax is 0 because there is no other horizontal forces. For ay, since it is the loads are acting distributedly equally, you can add all the loads here and you can uh, divided by 2 because it is shared by ay and dy. So 3 plus 2 plus 3 is 8 divided by 2 for 4. Or if not, you can get the moment at point A or B and it will give you the same answer. So for point A, uh, at point A, you have member AG and AB. Okay? So you have AG and AB. So only the forces and half the members have to be determined. Since the truss is symmetric, meaning if we can determine the forces acts on AG, AB, GB, GF, and BF, it will have the same member force at the other side because this is symmetric. Okay? So if we use point A, summation forces along Y is FAG sine 30 downward, so negative, then 4 kilonewton positive. Force AG will become 8 kilonewtons. It's compression because it pushes the joint. Summation forces along X, FAG cosine 30 is negative, then FAB, so FAB is 6.98 kilonewton tension because it's pulling the member. The same with point G and point B, just follow the correct direction. Actually, there is no problem about the direction because if there is a wrong sense of direction, it will just give you a negative answer. But of course, the magnitude will be the same. So just follow the procedure with point A, G, and B, and everything will be the same. How about this one? Determine the force in each member of the truss. Indicate if the members are in tension or compression. Assume all members are pin connected. So we will use again uh, the joint method of joint. So again, here this is not distributed equally, so we need to determine all the forces and we cannot do the same with what we did in the previous one. So instead, you can have moment here at point A to determine dy. Okay? The same is true with A. You can have moment here to determine ay, and summation forces along x, ax is 0 because there is no horizontal reaction. So here, yeah, summation forces along D. So ay times 8 plus 8 plus 8, 24, minus 2 times 8, 2 times 16, 1.5 times 24, it will give you ay is 2 kips, ax 0. Then now you can have point A. Okay? So at point A, summation forces along y. So 2 upward minus FAH times 1 over square root of 5 because we are considering the vertical component of FAH. FFH is 4.47 kips compression. Then summation forces along X. FAB minus FAH 2 square root of 5. FAB is 4 kips tension. Okay. Then the same for all, and this will be the answer. Don't worry, I will send the PowerPoint so you can check or you can verify all these answers. The same, so no need to discuss point by point. Let's proceed. Method of section. So if the forces in only a few members of thrust are to be found, so for example, you are required to determine one force member only. No need to use the method of joint. You can use method of section. So for method of section, make a decision as how to cut or section the thrust through members. Then, before isolating the appropriate section, it may be first necessary to determine the thrust external reactions. The same, even in method of joints, you need to determine first the reaction, then draw the free-body diagram of that part. Always assume the unknown force acting on the joint free-body diagram is the same to method of joint. Moment should be some about a point that lies at the intersection of the line of action. If two of the unknown forces are parallel, forces may be some perpendicular to the direction. So determine the force GG and GO. Where is that? GJ and CO. So if you use method of joint, there is no problem about it. But remember, we want to determine only two force members. So I think method of cut is more easier to use. So I cut it. So member GJ can be obtained by considering section AA. GJ considering section AA. So I isolate this one. Okay. Did you see? GJ. This is the unknown. So you can get summation forces along I. So FGJ, if this is 30, meaning this is 30. FGJ sine 30 upward, meaning this one. Sorry, this one. Times 6. Then 300 times the distance between 3.464. FGJ is 346. If you get moment here, the forces GH, KJ, including at point I, will become 0. How about the other one, CO? CO. Get summation forces at summation moment at A. 300 times 3.464, then CO times 6. FCO is 173 pounds.